Welcome everyone. Today we're going to speak about controllability and observability, and specifically today I want to give the physical and geometric meaning of controllability and specifically the Gramian matrix. So let's begin with just a summary of what we did in class. So first of all, we spoke about controllability and we introduced a new notion, the notion of controllability in Gramian. So it's defined as follows with this integral. Now, the fundamental theorem of this lecture is that the system is controllable on this interval t0 up to t1. Actually, it's if and only if the Gramian at time t1 is non-singular. And this of course means that the system can be steered to any desired state using some input. Now we also know that actually the non-singularity of the Gramian is equivalent to the Gramian being positive definite. So instead of checking that the Gramian is non-singular, we can check that it is indeed positive definite. Now specifically for LTI systems, the integral is a little bit nicer, you could say. We have this notion with the matrix exponentials. Now, what is the meaning of this Gramian is what I'm going to speak about today, but overall, this Gramian helps us quantify the control effort. So it more or less measures the energy or the effort required to steer the system in any direction of the state space. Okay, so we're going to really deep into this in a moment, but just let's go over observability first. So we have similar notions. So the observability Gramian is defined as follows, and similarly the system is observable on interval t0 up to t1 if and only if the Gramian at t1 is non-observable or invertible, it's the same. And again, the Gramian will be non-singular if and only if it is positive definite. So instead of checking for non-singularity, we can check for positive definiteness. It's all the same. And specifically for observability, we know that the notion of observability in LTI cases is time independent. That's also true for controllability, and we also have the Kalman test for observability, which we saw in the previous course, and this is also the same for controllability. If the system is LTI, we can also use the Kalman test. Okay, so now, what is this Gramian? I remind you that we define the Gramian as follows, and in the controllability proof, we chose our input to be this specific U. Now, this is not a random choice. This is a very, very important choice of input. It's the optimal energy input. So what does this mean? Let's go over it. Let's imagine we want our system to move from some current state to some target state with minimum possible effort or minimum energy. So we want to define our cost or our energy, and the cost will be half integral over the norm of our input squared. The input is what we give into the system, it's our effort, and this is quite a basic notion of energy. As you might remember in physics class, when we had some ball move around in a line, so its energy was x squared over 2, and that's basically, it's the same notion. Just because u is a vector, we need to use the norm and not just put u squared, but it's the same idea. Okay, so what is our constraint? Our goal is to reach point x1 at time t1. We know that the solution of our system at time t1 is this homogeneous part plus this integral part, and here all I did was just compare it with x1. That's our goal, that's the target, and I just moved the homogeneous part to the left. So let's call this left part, which is like the required movement, delta x, and let's call the expression inside the integral age of tau. So age of tau is some matrix. Then this expression, this becomes the following constraint. We have the integral over h tau u tau equal delta x. Now in standard calculus, specifically calculus 2, to minimize a function fu subject to a constraint gu equal to some c, we form this Lagrangian. And I'm sure you saw this many times in calculus 2. We had a function of two variables, x and y, and we had an additional constraint. So like questions of the form, find the minimum of these two variable functions on a box or with some constraint. So we would build this Lagrangian, and then we would differentiate with respect to x, with respect to y, and compare with 0, and then finally with respect to lambda and compare with 0 to actually take into account the constraint. This is exactly the same, and the only difference is that lambda now is a vector because f is also a vector, everything is a vector here. But it's the same basically. So let's write our Lagrangian. We have the cost, clearly norm to the power of 2 is just the inner product between u and u, so u transpose u, it's just some scalar, and this is our constraint, so this is the Lagrangian. Now, because lambda does not depend on anything, I just put it inside the integral, and I can just combine these two integrals into one expression. So I can rewrite the Lagrangian as follows: the integral of some expression, the tau, minus lambda tau delta x. Now our goal is to minimize this. This has to be as small as possible, taking into account that we can only control u. We only put in the input. We cannot control anything else. Clearly, in order to minimize this integral, the integrand must be as small as possible. So what I want to do is I want to focus on the integrand, so let fu be some integrand, and we want to minimize it, again with respect to u, because it's the only thing, it's basically the only variable we control. So just like in calculus, we differentiate with respect to u and compare with 0. Here it's a little bit different because u is a vector. Again, u transpose u is a scalar. Age is a matrix times u is a vector. So we have lambda tau, which is a row vector, times a column vector, which is also a scalar. But when we differentiate a scalar by a vector, things are a little bit different. This is what we obtain. To explain why I have this remark, so we have a remark and also an example. I don't want to go over it because you have these notes, you can go over them, but basically the point is that because we are differentiating a scalar with respect to a vector, is we just differentiate the scalar with respect to each element. So this also gives a vector. Okay, so let's continue. We want to solve this. It's quite easy. We just get that u is equal to minus h transpose lambda. Substituting back that h is actually our transition matrix times b, we obtain that u is minus b transpose phi transpose lambda. Now remember, in class we let u be b transpose phi transpose u bar, so basically we just obtain the same expression, and in class we let u bar just be minus lambda. U bar is some vector, so u bar or minus lambda, it's the same, it doesn't really matter. So to conclude, this u bar is not just random choice which works for the proof, it's actually the input that will actually take us from one point to the other using the minimum amount of effort. This is very, very important. Okay, so we actually defined effort, we defined the energy, we actually found the input for which we will use the least amount of energy or effort. Let's check what's the energy. So to do it, we just plug in our U. So U is again B transpose phi transpose U bar. Here it's the same with the U bar transpose. And now remember that the proof actually gives us U bar. So U bar is the inverse of the Gramian times x1 minus phi times the initial state. So we can plug this in. Now, because we are dealing with control and with the inputs, just for simplicity's sake, let's assume the initial condition is 0 and our target again is x1. Since the initial condition is 0, this expression is also 0. So specifically here, U bar is the inverse of P times our goal, our target. So we plug it back in inside here and here, and we have this expression and this expression. Now note that by definition the Gramian matrix P is symmetric. You can clearly see it here. It's defined by something times its transpose. It's always symmetric. This means the inverse is also symmetric because of this expression. We know this holds, and this implies that if a matrix is symmetric, the inverse is also symmetric. So we can just remove this transpose over here, and we are left with this expression. Now also note that x1 P inverse here and also here, they do not depend on tau. We integrate with respect to tau, so we can just take these two expressions out, and we obtain half x1 transpose P inverse times this integral, which is exactly the definition of the Gramian, times the inverse times x1. So this is what we have. Now P times P inverse just cancels, and we are left with half x1 transpose P inverse x1. So we conclude the optimal energy is half x1 transpose P inverse x1. Let's say we want to move from some point, in this case just from the origin to some point x1. The least amount of energy we can use, or least amount of effort we can put into this movement, is exactly this expression given by the inverse of the Gramian matrix. So this equation is actually the physical definition of the Gramian. So let's just go over it. Basically, P itself is like the ability. It quantifies how easily the inputs can affect the states. The inverse is the inverse. It's the resistance. It quantifies how much energy the system resists your efforts to move it. So this is why the inverse gives the notion of energy. Now basically, if P is singular, so we cannot even invert it, it has a zero eigenvalue. This means that the inverse effectively it has an infinity in that direction. It's like it has an infinite eigenvalue. Basically, this means that we require an infinite amount of energy to move in a certain direction, which is like saying we cannot really reach this direction. So that's why the system is uncontrollable. Let's dive deeper into the geometric meaning of all of this. Imagine we are limited in our energy. We have fuel, we have a limited fuel budget. Let's say we have 1 unit of energy. What is the set of all possible states we can reach? So the set of reachable states is defined as follows. We know this is the energy, and we have a budget. The energy is limited by 1. This is actually an ellipsoid, a stretch sphere. This means that actually the eigenvectors of P point along the axis of this ellipsoid, and the eigenvalues determine the length of these x's. So to make this clear, let's just take a 2 by 2 example. So n equal to 2, we can always diagonalize p because it's symmetric. So p is phi lambda v transpose. Lambda is just a diagonal matrix with lambda 1, lambda 2. V is just v1, v2, where v1 and v2 are the eigenvectors, of p. The inverse is just the inverse of this thing, which becomes this expression. So we have v lambda inverse v transpose. We plug this back here, and we have x transpose times this expression times s less than or equal to 1, and we can regroup this expression. So if we let x tilde be v transpose x, then we obtain a much nicer expression, which is x tilde transpose lambda inverse x tilde less than or equal to 1. And clearly the inverse of a diagonal matrix is just taking the inverse of each diagonal entry. So here we have 1 over lambda 1, 1 over lambda 2, and to summarize, this is what we get, and we actually go through with the multiplication. So we have first this and then this. Okay, this is exactly the formula for an ellipsoid. Okay, this is the formula for an ellipsoid, and the radiuses, the semi-axes, are exactly square root of lambda 1, square root of lambda 2. And this is how this looks. So we have this expression. Equality is clearly for the circumference, the inequality is for the circumference and everything inside. So x1 and x2, which are related to the eigenvectors of p, will give the direction of the x's, and here we have these semi-axes. Now, basically, when we speak about controllability, we assume we have an infinite amount of energy. What we did over here is, okay, let's say we assume we have 1 unit of energy. This tells us where we can travel in space. General controllability assumes we have an infinite amount of energy. So the ellipsoid becomes the entire space. And this is exactly controllability. This means the entire space is reachable. Okay, just to emphasize, this ellipsoid actually gives me the reachable space. With 1 unit of energy, I can only reach inside this ellipsoid. And again, if my energy is endless, is infinity, this ellipsoid becomes the entire space, and this is exactly the definition of controllability. Okay, so let's go back to what we saw in class. So we had a motor control of a drone, and there we obtained that the Gramian matrix is T1 minus T0, 0, 0, T1 minus T0. So if we let delta T be T1 minus T0, the eigenvalues are clearly delta T, and then plugging in lambda 1, lambda 2, we have this expression, which actually just turns into a circle or a ball with radius square root of delta T. So this means that it costs the same amount of energy to move 1 meter north or south as it does to move 1 meter east or west. The system is equally controllable in all directions. Now, the more time we have, the larger delta T is, the further we can travel with the same amount of fuel, because it's basically, we just increase this circle. Now, what is the cost of reaching some point? So basically, I just take some general point, x1, x2, plug it inside our expression for the energy, and this becomes 1 over 2 delta t x1 squared plus x2 squared, which is just 1 over 2, basically the distance squared over delta t. So basically, the further away we need to go, the more energy we need to spend. This is quite natural. Now, the more time we have, the less energy we need to spend. So assume we need to travel from New York to Boston, and let's say I only have like 1 hour to make the ride. So I need to go really, really fast and therefore use a lot of energy. Let's say I need to go from New York to Boston and I have like a week. I can travel at like, I don't know, 10 kilometers per hour, get there in 2 weeks and spend not a lot of fuel. So this is the meaning of what we have here. Now, what is the optimal fuel control? So let's plug everything inside our expression for u. Now, in this example, as we saw in class B, is equal to phi is just the identity, and if we let delta x be x at t1 minus x at t0, we obtain the following. So this is what we have, and we end up with delta x over delta t. This means that the velocity for which we spend the least amount of energy, first of all, is constant. This is a constant vector, and it's actually just the average velocity. And it quite makes sense. To get from point A to point B with the least amount of energy, we just need to go with average velocity. Now let's go back to the example where the y direction is damaged. So let's assume we can only output 10% of the force in the y direction. In this case, matrix B becomes this matrix. A computation gives this Gramian, and the ellipse is given here. So we can see that one direction is more stretched out than the opposite direction. So what does it mean? It basically means it's easier for us to travel along the x1 axis than it is to travel along the x2 axis, and this makes more sense. We need to spend more energy going along the x2 axis, so we can travel less far. Now let's just assume how much energy do we need to exert to reach some point 1, 0. So if we plug everything here inside, we obtain 1 over 2 delta t. So this is traveling along the x1 axis. If we take x at t1 to be 0, 1, we obtain 1 over 0.01 twice delta t over here. So we obtain 100 times 1 over 2 delta t. So because our motor is damaged in the y direction and we can only output 10% of the total force, we need to use 100 times more energy when we travel in this direction. This is what we obtain. Now, what is again the optimal control? The optimal control in the x direction, in the x1 direction, it's the same as before. We just follow the average velocity in this direction, but for the x2 direction, we need to put out 10 times more velocity to move in that direction. Now, finally, let's say the motor is dead. So let's take B to be 1, 0, 0 epsilon, where epsilon goes to 0. Now a calculation gives this Gramian, and the ellipsoid is given here. Now, basically, as var epsilon goes to 0, the ellipse collapses into just a flat line segment. So, because this thing goes to infinity, and it's the same as like having one flat line. This means we can only go along the x1 axis and we cannot at all go along the x2 axis. This makes sense. This also implies the system is not controllable. Now the eigenvalues is delta t. So this is the standard case in x1. And the second eigenvalue is epsilon squared delta t, which goes to 0. So we have 0 reach in x2. Now again, if we take our target to be 1 and 0, we have the same amount of energy we need to spend. And if we take our target to be 0, 1, the energy we need to spend is 1 over epsilon squared, and as epsilon goes to 0, the energy goes to infinity. So if we need an infinite amount of energy to go someplace, this means we cannot really go over there. So the system is uncontrollable. So let's just go into the interactive section. So basically here we have sliders to control the eigenvalues of the Gramian. We can also control the rotation, which is like controlling the eigenvectors. And these two is the target. So I can actually choose the target and I can choose the Gramian, and here over here we have the reachability ellipsoid, the reachable space, and here we actually have the control required to actually get to the target. So you see, sorry, I need to play it. One moment. Okay, so we have 0 rotation. I can play with the eigenvalues and I can change the ellipsoid. Note that this ellipsoid is the reachable space for 1 unit of energy. If my target is outside of the ellipsoid, it just means I need more than 1 unit of energy to reach the target. If the target is inside my ellipsoid, this means that with 1 unit of energy I can actually get to the target. And note that the control input is almost always in the direction of the target. Makes quite a lot of sense. Now, when the eigenvectors of P change, then the ellipsoid actually rotates. So it's quite interesting that, let's assume this is the target. For some eigenvectors, the target is reachable, and for other eigenvectors, the target is not reachable. So it's like, it's a play of both eigenvectors and eigenvalues. Now regarding to energy, so let's play this part. So basically here I'm referring to the example with the drone. So we have the normal motor in the x1 direction, and we have the damage motor in the x2 direction, and the z is just the amount of energy we need to put in. So note that the more time we have, the less energy we need to reach one place or the other. And this second slider is motor efficiency. So the less efficient the motor, the more energy we're going to need to spend to reach our target. So it makes sense. And again, as I increase the time, I reduce the energy. Because if I have a lot of time, I can use a lot less energy to get from one point to another. Now, let's go back and analyze the Gramian again, because, okay, where does it come from? What does the Gramian mean specifically? So again, because we are studying the impact of control, let's assume the initial value is 0. Then the solution of the system is as given here. Now, let's assume our input is an impulse at exactly time t equal t hat. So u is delta t minus t hat times some u hat, which is, it's a constant vector. It's basically, it's just some direction. So we want to kick the system in some direction at time t equal to t hat. Now, if we plug u here, this is what we have, and by the definition of impulse, this integral becomes this notion. So if we kick the system in the u hat direction at point t hat, the system at time t will be this expression. Okay. Now, the Gramian is exactly this. So the Gramian is v tau times v tau transpose, where v is exactly our transition matrix times b. So what does the Gramian actually mean, since we integrate over times? Basically, each time is a kick at time tau in some direction. The Gramian p sums these kicks over all times. So we sum over all times the power from kick at time tau. Okay? When I take some vector and multiply it by the transpose, we have a notion of power. Similar to what we did earlier when we had u transpose u, so we get a scalar which represents power, and v transpose is a matrix which represents power. Basically, each entry is how much power I need to spend going in each direction. So the Gramian sums this. So basically, B is input power. This is the energy, the raw energy we are pouring into the system. And P is the result. After pouring power in for t seconds, how much of that energy actually stuck to the system and converted into movement. And the controllability Gramian is a matrix that aggregates all control opportunities over a time interval to quantify exactly how much energy is required to steer the system in any direction of the state space. So here we have it. We have a lot of physical and geometrical interpretations to this Gramian. It's not just some mathematics trick. It has a lot of insight and a lot of meaning, and it can actually give us the reachable space given some constraint on energy. And that's it for today. Thank you.